Welcome back to this NPTEL online certification course on reactive intermediates and molecular arrangement. In the last class I was talking about carbene. I have introduced the singlet triplet carbene. I have introduced their their bonding, their structure, some of the different reactivities. In the today's class I am going to specially focus on various different reactions using carbene. So I am going to start with the addition reaction. I am going to show you what is the difference of singlet and triplet carbene once it adds to the olefin. Then I am going to talk about the Simon-Smith reaction and various different example, and there are some diastereoselective reactions I am going to talk about. Also I am going to talk about some enantioselective version of that. Then I am going to talk about the insertion reaction using carbene. I am going to introduce you to the carbenoid and carbene, the metal based carbene I am going to introduce you. So let us start with the addition reaction which you want to start. So in this course I am going to start with the addition first and then going to the insertion reaction, and then finally I am going to talk about the rearrangement. So first thing we are going to learn that once the singlet carbene add to the olefin, why this reaction is stereospecific, but once this reaction happen with triplet carbene, the reaction is not stereospecific. So to explain that, let us take an example here. So here we are talking about generation of dibromo carbene, which is generating from CHBr3 using potassium tarbute oxide. So using the Z alkane, it is giving the cis isomer as a major product, and then using the E alkene, it is giving the corresponding trans isomer as a major product. So why that is happening? So let us try to understand the reaction. First, I think the formation of this singlet carbene is well understood. I have already explained about this alpha elimination in the previous class. So after formation of the singlet carbene, it actually react with olefin through a concerted process. You can see this CBr2 carbene has this 2 electron in the opposite spin, and the double bond also has the 2 electron in the opposite spin. So they react in a concerted manner to form the corresponding product. That is why as the reaction happening in a concerted manner, so that is why the reaction is very stereospecific, giving the cis isomer from the Z alkene, and very similarly if you start with E alkene, it is forming the corresponding trans isomer. So now we will try to understand what is happening in case of triplet carbene. So here is an example of triplet carbene which is forming from this fluoryl diazo compounds. So now what is happening, now once it is reacting with the Z alkene, instead of forming this corresponding cis isomer as an exclusive product, what is happening, it is giving 65% of cis isomer and 35% of trans isomer. So now we will try to understand what is happening in the reaction mechanism. So first thing is, once this carbene is forming, this is a triplet carbene. So first the carbon-carbon bond formation is happening here, so we can understand this clearly. Now there is a problem. Now these 2 electrons which is supposed to form bonds are actually have a same spin. So there is a spin flipping is required for formation of this bond. So when the spin flipping is happening, as this process is slow, in the meantime there is a free rotation happening between this carbon-carbon bond. Okay. As there is a free rotation happening, now these 2 methyl which was initially in the cis, now they become trans after the free rotation. So now starting from this intermediate, it can go for the spin flipping, and then after that it can forms the bond to make this corresponding cis isomer. At the same time it has already this particular intermediate. From there it can form a bond here and form the corresponding trans. So because there is a spin flipping happening, at the same time there is a bond rotation happening. Okay, so that is giving the mixture of cis and trans. So here we can explain them through the molecular orbital diagram, that when this is approaching. So there is 2 different approach we can explain. One is the direct approach, and one is the side on approach, which we have explained here. So we can explain the both of these things in this slide. So what is happening here, if you try to think about the direct approach, which I was trying to show you in the previous slide, which is not favorable, because if you see a alkene homo and a carbene LUMO, then in one case there is a bonding interaction between this, but in other side there is a other side of this lobe there is a anti-bonding interaction. And if you consider the alkene LUMO with a carbene HOMO, in that case also we are seeing one side there is a bonding interactions and other side there is an anti-bonding interaction. So that's why the direct approach of carbene to the olefin is not favorable, but if it is go for a sideways approach, that is favorable. So what is do mean by the sideways approach? Now if you try to draw this carbene in a sideways approach to the, it's coming to the olefin, now in both the side it is forming a bonding. Okay. If you take a alkene LUMO and the carbene HOMO, also we are seeing the very similar thing, there is a bonding interaction happening. Okay. So now I am going to talk about the the generation of carbene from diazomethane. I think I already talked about that. What is happening, that under light what is happening, it is forming a singlet carbene at the first, and it is forming this corresponding product in a stereospecific manner, once it is reacting with the olefin. But here what is happening, once you use a photosensitizer like benzophenone, then it is forming a triplet carbene. So now you can see it is giving a mixture of cis and trans product. Okay. So in the previous class I have already talked about the generation of singlet and triplet carbene, but you can verify that by reacting with the corresponding olefin. So now I am going to move to the Simon-Smith reaction, one of the very important reaction for the synthesis of cyclopropane, and this reaction was applied for several natural product synthesis. So using this zinc copper couple and then using the diiodomethane in ether, it can convert this corresponding double bond to the cyclopropane. Okay. So again what we are seeing here, from corresponding cis olefin we are getting the corresponding cis product, and from trans we are getting to the corresponding trans product, which kind of suggesting that the carbene which is forming are actually in singlet in nature. So there is a modification by Furukawa's group. So what they found, that they replaced this zinc copper couple with dialkyl zinc. Using the diethyl zinc also this reaction is possible to convert the olefin to the cyclopropane. There is another modification by Sarate group. So they found that instead of CH2I2 they can replace by aryl diazo compound. So this aryl diazo compound can also go for the diazo decomposition, and then after reacting with the zinc iodide they can form this corresponding starting material which is a carbenoid. As you know, I think I am going to discuss about carbenoid in the later slides, that it's actually a carbon which has 4 different groups, and one of them is a metal, and one of them is a living group. Okay. So this carbenoid now can be reacting with this olefin to form this corresponding cyclopropane. So now I am trying to show you the mechanism of this reaction. As I said, the first this corresponding carbenoid which is going to form after the zinc got inserted between this carbon-iodine bond. This carbenoid is reacting with the olefin. So what is happening here? Literally you can see this once the zinc, so this this zinc carbon bond, this carbon has some sort of a carbon property. It is giving the electron density to this pi star orbital of this pi bond, and at the same time there is also this carbon-iodine bond is getting eliminated to form a cyclopropane. It goes via a butterfly type tangent state, okay, to form this corresponding cyclopropane. Again using the dialkyl zinc, what is happening? Dialkyl zinc react with this diiodomethane to form these compounds. Now after that it can so again it is forming this corresponding carbenoid which is reacting with this olefin through this butterfly like tangent state, it can form the corresponding cyclopropane. So here is an example. Now we are talking about the electronics. That means you have 2 different olefin. One is electronically deficient, another is not electronically deficient. Okay, so that is you can say electron rich. So that means now the reaction is happening to the electron rich one, not the electron deficient one. Here is another example, also very similar thing, electron deficient and this is electron rich. So the reaction is only happening to the electron rich olefin. So here is an example. Here we can talk about that you have olefin. One is a terminal olefin. So one is one which is internal. So this is an alene. So now the reaction is happening to the internal one, because you can see the internal one is actually is electronically rich compared to the terminal one. There is another example here. You have a OTMS ether versus a terminal olefin. So this is an interesting example, because you can see the OTMS ether is getting electron density from the OTMS group. This double bond is getting electron density. So this is electronically rich. That's why the cyclopropionation is happening in this position. Of course, I think in this reaction there is also mixture of product forms. So this is the major one, and then there is there is other product where you get the cyclopropion formation happening both here and in this position as well. Okay. So now I am going to talk about very interesting things, the diastereoselectivity in Simon-Smith reaction. Okay, what is happening if you start with this corresponding allylic alcohol. This allylic alcohol is you can see this alcohol, this oxygen is actually up. So now what is happening, the cyclopropion is forming at the same side of this OH group. That means what is happening, the OH group acting as a directing group for this reaction. So it is actually coordinating with the zinc, that is allowing the cyclopropionation happening to the same phase of this OH group. Okay, so that means that's why we are ending up with this product with 99% of this diastereomer is forming. A very similar thing happening here. You can see this OH group also acting as a directing group for the cyclopropionation to happening in the same side of the OH group. Another example here, I think after opening up this epoxide, it is forming this compound, this is allyl alcohol. Again this OH acting as a directing group. There are some more example. Again I think in this one, I think you can see there are two different scenario. You have one is alpha beta unsaturated ketones, that means this double bond is electronically deficient. You have another side allylic alcohol, which is which is going to take part in the cyclopropionation, and OH is acting as a directing group for this diastereoselective reaction. There is another case here. You can see this ester group can also act as a directing group to form some sort of a bonding with the zinc. So there is ester oxygen going to form a bonding with the zinc for the cyclopropionation in the same side of the ester. There is another example here, because if you have a cyclopropan here, what is happening now, the cyclopropionation is happening to the other side to avoid a steric interaction. So here is an example of asymmetric, so I talk about the diastereoselective. Now I am going to talk about asymmetric example here. So starting from this corresponding allylic alcohol, they can able to get to this corresponding cyclopropane with 98% EE and 50 to 1 diastereomeric ratio. So what is happening here? Let's try to understand. So you can see in this reaction, the important thing is you need to use the Simon-Smith condition with you have to use this chiral ligand. In this chiral ligand, you have this boron here, which is actually attached with the chiral diol. So now in the transient state, the important thing is happening, the zinc actually getting coordinated with this oxygen of this carbonyl group. It is also coordinating with this oxygen of this, which is next to the boron, and this allylic alcohol actually first reacting with the boron and forming this complex. Then zinc is also coordinating with the oxygen, forming some sort of a chiral complex. Okay. Because now what is happening, because of this coordination, this cyclopropionation happening only one particular phase of this olefin. As you know, olefin has two different phases, but because this zinc is getting coordinated with this chiral boron, so this cyclopropionation happening with a particular phase which is shown here to get to this corresponding product. So now some application of this cyclopropionation reaction in the natural product synthesis. As I told you at the beginning, you can see there are olefins here, C2 symmetric. So it can form a cyclopropane first, and then after some steps it can form this corresponding natural products. There is another example here. You can see there is this olefin here which can form cyclopropane under the Simon-Smith condition, and then further after few steps it can form the corresponding natural products. There is another interesting example here. You can see this one has several different olefin 1, 2 and 3. But now once you are using this condition where there is some sort of a coordination with oxygen going to happen with the boron. So the boron is going to coordinate with the oxygen of this boronic ester. So then what is going to happen? Then the cyclopropionation is happening selectively on that particular position because of this OH group. So this is acting as a directing group to activate to get the cyclopropionation selectively into this position once you conduct the reaction at low temperature. So once you are conducting the low temperature, now this type of effect is getting prominent. So now I am going to briefly talk about the metallocarbene. I think the metallocarbene is not part of this course. There are other NPTEL lecture which is covering the metallocarbene. I am going to just briefly talk about, there are two different metallocarbene. One is the Fischer carbene, another is the Schrock carbene. One of the important thing is that the Fischer carbenes actually are singlet carbene, and the Schrock carbenes are triplet carbene. Now what type of transition metal is participating in the Fischer carbene? You can see middle and late transition metals, okay, with a low oxidation state. That is the other important thing. Like we have given some example here, and the ligand has to be a pi acceptor. That is another important thing, okay, for a Fischer carbene. I have already shown here in this diagram, and then there will be a pi donor substitution. So this type of metal carbene complex is called Fischer carbene. Then other side on the short carbene, there has to be early transition metal with a high oxidation state, and then there should be a non-pi acceptor and non-pi donor, okay, non-pi acceptor metal ligands and non-pi donor substitution. So they are going to form a short carbene, okay, which is also shown in this diagram. So now I think why I have introduced you to the metallocarbene, because there are a lot of cyclopropionation which is done using the metallocarbene. Okay. In this type of transition metal catalyst cyclopropionation, what is happened generally, this diazo compounds are used. So what is going to happen, those diazo compounds are actually going to form the metal carbene, which actually react with the olefin to form cyclopropane. There are two different pathway. It can either go to, goes by this concerted pathway, where it can form some sort of a 4-member intermediate, their 4-member transient state I can say, and then goes to the product, or it can go via some sort of a stepwise mechanism to a electrophilic attack, and then finally this bond can come here, and then getting out the metal to form this corresponding cyclopropane. So I have tried to give you an example here from the diazo compound. If you once use these transition metals, they form the first thing called carbenoid. Okay, so we should be careful when we say metal carbene versus carbenoid. So these are the things called carbenoid. As I said, the definition of carbenoid, the carbon is in tetravalent, one of them is in the metal, and there is a leaving group, okay, which finally after the N2 extraction it can form the corresponding metal carbene, which can take part, very similar to this Simon-Smith reaction. You can see this can also take part in the cyclopropionation reactions. Like as I mentioned, there are either it can goes via a concerted mechanism or a stepwise mechanism to form this corresponding cyclopropane. So here is an example about the the rhodium tetraacetate. So rhodium tetraacetate, you have this axial position where this diazo compound can get attacked here, and then after that it can, after that in eliminating of the nitrogen, it can form this corresponding rhodium carbene complex, and this rhodium carbene complex can react with the olefin to form the cyclopropane. Then this can happen using the copper. Very similarly, it can form some sort of a carbenoid species, then goes to the copper carbene. From there it can goes for the corresponding cyclopropane. So here is some example using copper. You can see using copper metal it can form the corresponding cyclopropane, but the problem is in this type of reaction using copper for the cyclopropionation using the diazo compounds, the diasto selectivity is not very good. Okay, but here what is happening, it is forming this corresponding exo product as a major product, because this is a thermodynamic stable product. Then there are some example using the rhodium. Now you can see from this phenyl ring it can react with one of the olefin, then after that it can go for electrocyclic ring opening to form this compound, okay, which is shown here. So then there is other example here. I think again the the rhodium carbene can be formed corresponding diazo decomposition. Then there is a olefin here which can forms a cyclopropane to make some sort of a strained molecule. Then I am going to introduce you another important reaction of this type of metal carbene species called the insertion reaction. So first thing I am going to explain you very basic reaction here. If you see in this compound, once you use the sodium methoxide, now this proton can be abstracted for the E2 elimination. It can form these particular compounds. Now once you treat this compound, instead of the sodium methoxide, if you use this phenyl sodium species which have a pK 50, then it is ending up forming this, where you can see one of the deuterium is missing in the product. Let's try to understand what is happening here. So once you using the strong base, it is going for the alpha elimination. It is cleaving this carbon deuterium bond, generating a carbon ion, going for alpha elimination to generate a carbene. After formation of carbene, there is this CH insertion is happening. So we call this 1,2 migration, or there is a deuterium suppling is happening to end up this product. We can understand this from this orbital diagram. What is happening here, you can see this sigma bond, this sigma CH bond is drawn here, is giving electron density to the empty orbital of the carbene. So, there is a empty orbital in the empty p orbital in the carbene, where this sigma CH bond electron density is transferred. Okay. And then what is happening at the same time, there is, you can see there is a field orbital, field electron, which can field pair of electron getting transferred at the same time. So, once you are drawing this, you can write that way, that first this bond is getting here, this electron density, and at the same time this is coming back here to formation of this type of olefin. So, again we are explaining that this type of reaction, what is happening, this is a CH HOMO and then the carbene LUMO, and you can see in the both cases there is a bonding interaction happening here. Also, if you start from the CH LUMO and the carbene HOMO, also we observe there is a bonding interaction. Once they are interacting in a sideways overlap to form this, so after the CH insertion it can form this type of corresponding product. So, here is an basic example, that if the tungsten metal based carbenes was used, then you can see here first thing is the the diazo decomposition happening and the generation of the tungsten metal based carbene. So, after it forms the, so this is a carbenoid, then N2 release, formation of the tungsten metal carbene. Now, this XR, it could be any type of heteroatom which can interact with this, the metal from this type of tangent state, from there it can goes to the product and the metal goes back to the system again. There is an example here. First thing we can see there is a CH insertion happening. So, first thing again generation of corresponding carbene here after the alpha elimination, it can take this proton from this methyl group to form this corresponding cyclopropane. Okay. We can see another example here using this type of tetrahydrofuran, then using this diazo compound and the copper catalyst. So, again there is a insertion happening of this CH bond is getting inserted to form this corresponding product, which is actually the next to oxygen. So, now we are going to talk about a intramolecular version here. So, now once this intramolecular CH insertion happening, one of the important fact here, they are end up with this particular product where this ester and these groups are actually trans. So, now we try to understand why this insertion getting favorable and forming this trans product. To understand that, we have to go to the corresponding tangent state where this reaction is happening. So, after the formation of this corresponding carbenoid, which is here, after the N2 expulsion happening is forming the corresponding rhodium carbene. Now, you can see in this tangent state where this CH insertion is taking place, this ester group and this group, these two bulky group not going to be in the 1,3 diaxial position. They will try to be in the anti position, so that they do not have to face the some sort of 1,3 diaxial interactions. To avoid that, you can see these groups and these groups are in the opposite side, which end up giving the product as a trans. So, now the question comes, in these reactions, if you do not have anything else, suppose you have a solvent in the medium. Now, once this type of carbene is formed, these are very reactive, it can take the solvent molecule. So, CH insertion happening in the cyclohexane to get to the this type of product. Okay. Now, we can see this type of reaction can also happen with the alcohol. Okay. Once you take the alcohol and then once you take this corresponding diazo compound, in presence of rhodium catalyst, again it forms the corresponding rhodium carbene, and then this so I think I have talked about this oxygen lone pair can give electron density there, and then finally it can form this corresponding product. There is a NH insertion happening here after forming of this corresponding diazo compound. Once you treat with the rhodium catalyst, what is happening? Again you can see this nitrogen has a lone pair which can give electron density to this corresponding the rhodium carbene, and then this minus can catch this H to form this corresponding beta lactam. Okay. So, in this particular part, I think I started with talking about different type of reaction. So, initially I start talking about the formation of the cyclopropane, and then I was talking about the Simon-Smith reaction. I talk about the the diastereoselective version. I talk about if you use a chiral ligand, then you can also make this reaction enantioselective. Then after covering that part, I also moved and talk about the what is called the metal based carbene and the carbenoid. I introduced the terminology, and then I explain some cyclopropanation using tungsten metal, and then also talk about some more example of the cyclopropanation, and then some CH insertion reaction. In the next part, I am going to talk about some of the rearrangement reaction done with carbene. So thank you all, and thank you for coming to the class. Thank you.